So we have 2 lectures on oscillators on YouTube. And by that time, I hope you'll have enough time to watch those lectures. And of course, there will be an incentive to watch those lectures, because next Tuesday again, there will be another class test. And this class test will be on oscillators and digital electronics. Not all of digital electronics, only the digital electronics that's covered in the first 2 lectures, that is the lectures for this week. So that will be on Tuesday again. So digital electronics and oscillators, essentially 4 videos. So any questions you have on oscillators, we will tackle on Monday. And today, what I want to do is talk to you about some digital electronic circuits, but that presumes that you have already gone through the first 2 lectures in digital electronics, which may or may not be true for all of you. Okay. So, but I do assume one thing. Suppose all of you know these things, right? All of you know what an AND, an OR, and a NOT are. When I say such a thing, I'm going to assume, when I say this, what I mean is, if you do not know what these are or have forgotten what these are, please speak up. Okay. It's possible to forget things like these. These are things you learned long ago in class 12, I guess. But I'm assuming that most of you remember what AND, OR, and NOT gates are, even if you have not watched the 2 videos, which essentially talk a lot about AND, OR, NOT gates and how to combine them together and so on. So I'm going to assume that everybody knows this, because this is going to be critical, because unless you know this, you will not be able to follow anything about what I'm going to say next. So if there is anybody in the audience here who do not remember what AND or NOT gates are, okay, just to sort of round up the thing, if you have 2 these are Boolean gates with multiple inputs, minimum of 2 for AND or, only 1 for NOT. So NOT is the easiest. It changes A to A bar, and Boolean functions can take 2 inputs, 0 or 1, and NOT simply changes 0 to 1, 1 to 0. So that's what NOT gates do. And the symbol for the NOT gate is essentially a blob like this, but a NOT gate always has an amplifier. And in any case, if we were to just put a blob somewhere in the middle of your circuit with lots of complicated components, almost certainly the blob will be nearly invisible. So to make it visible, you draw an amplifier symbol right after the NOT gate, after the actual NOT bubble. So this bubble here is what really signifies this NOT operation. The triangle here actually stands in for an amplifier, but we usually say this is the NOT gate symbol, because that's how it's always drawn, with the bubble followed with an amplifier sign. For the AND gate, you will have could have multiple inputs, not necessarily 2, could have more than 2. But the idea is simply this: if you have 2 inputs, for example, you have 4 possible input combinations. A can take any of the 2 values, B can take any of the 2 values. And this is the form in which we prefer to write, the order in which we prefer to write our inputs. Of course, that's not a surprise, because this is the decimal number 0. If you think of these as binary numbers, this is 0, this is 1, this is 2, and this is 3. So we essentially write down the numbers 0, 1, 2, 3 in general to the n minus 1, where n is the number of inputs, to the n possible input combinations. So 0, 1, 2, 3 here, 0, 1, 2, 3, 4, 5, 6, 7 for 3 inputs and so on. And we would like to write down the output corresponding to this. I hope everybody remembers that this is called a truth table, simply because Boolean statements which you have written down as zeros or ones could also take values, or would equivalently take values false and true. And here the A and B essentially has this property, that is true only when both inputs are true. So, or high only when both inputs are high, or 1 only when both inputs are 1. A or B, on the other hand, again, if we do it with only 2 inputs, will look somewhat like this. Again, the inputs will come in this order. And the output in this case will be 0 only if both inputs are 0. For all the other 3 cases, it will be 1. So when we say A or B, we actually mean either A or B or both. So when any of these 3 combinations are high, you get all 3 highs. So this is basically what the AND, OR, and NOT gate are. I hope everybody remembers them. These are the symbols. This is the AND. You write the AND with a dot, or sometimes just don't even write the dot. And the OR is written like this. So these are 2 arcs, and then there's a bent base here. And in Boolean, we write this as A plus B, although we should read this always as A or B and not A plus B. Okay, so this is the basic background that you will need to understand what we are going to talk about today. What we are going to talk about today are rather advanced Boolean circuits. The simpler ones, well, we have already 2 lectures in which we are going to discuss some of the simpler ones, or strictly speaking, not really simpler ones, but less advanced ones. What I'm going to talk to you about are somewhat advanced Boolean circuits, although they are not necessarily more complicated. Okay, and then, okay, before we go on to that, let me just ask all of you one question, which is this. How many Boolean functions with n inputs are there? So what's the answer to this question? How many different Boolean functions can you have where you're considering functions with n inputs? So that's a pretty straightforward question. So what's the answer to that? Yes?
None.
Hmm?
0.
How many?
0.
How many different Boolean functions? The answer is 0. Come on. You can
Everything.
see 3 of them right in front.
No, you said n inputs, right? But all will take only 2 inputs.
No. I mean, how many? Say, first of all will take 2 inputs is not true. You can see that NOT takes only 1. AND or takes 2, but this kind of AND or takes 2. You can easily have AND gates with 3 inputs or so on. All I'm saying is that if you have a given number of inputs, so you could have a gate like this. Okay, that's just a symbol, but this symbol stands for 3 input AND gate. A, B, C. The output is A dot B dot C. Sometimes we don't write the dots even. And this is a function which gives you high or true only if all of the 3 inputs are high together. If only one of them is high or 2 of them are high, if any one of them is 0, it's better to put it that way, then the output is low. Okay, so that's a 3 input gate. You can have a multi-input gates. There's no real problem. In fact, you can construct multi-input gates directly, and there are many integrated circuit chips which actually has 3 or 4 input AND gates built into them. By the way, this is not really an electronics question. The question that I've asked you is a simple mathematics question. Okay, let's forget about n inputs. Let's talk about 2 inputs. How many different Boolean functions can you have with 2 inputs? The answer to that, of course, can't be 0 because you can see 2 of them right now in front of your eyes, right? There's an AND and there's an OR. Both of them are 2 input gates. And they're different, right? Different functions. They're really, okay, I'm going to interchangeably use the name gates and functions, although at a mathematical level, we are really talking of a function which takes in 2 inputs and produces an output. A gate typically is a physical realization of that. A physical circuit which essentially does the same job that the function really says. Okay, so a physical circuit which will produce a high output only when both inputs are high and low otherwise. That's an AND gate. The AND function is a mathematical function. It's just a function which returns 1 when both inputs are 1. But we are going to use those words interchangeably. So, how many two-input Boolean functions?
Sir, 4.
Yeah. 4. Why 4?
Because we have AND and OR, and then we can add the NOT gate in front of both. So to get 4, right?
Yeah, but how do you know that's where it ends? You mean NAND and NOR?
Yes, sir.
Okay, those are the technical terms for those. NAND is not AND and NOR is not OR. But for example, I can immediately give you another Boolean function. All output 0.
So
Is that a
16,
function? 16. Why 16?
because for
Just
each 0, 1, 2, 3, what we have for each input A, B, we can have two values, 0 or 1. Same. So there are
okay.
4 values. So 4 and each has two possibilities. So 16.
Right. So that actually is the correct answer. The point is A and B, the moment you have two inputs, the total number of possible input combinations is 4. And in Boolean algebra, as in all of maths, a function is something which gives you an output, a well-defined output for every possible input. However, with Boolean functions, the real new thing is, or real different thing from functions on a real line, for example, is that there are only two possible output values for each input combination. So 0, 0 could give you either 0 or 1, 0, 1 could give you either 0 or 1, and so on. So there are 2 times 2 times 2 times 2. 16 possible different things you can put on the last column. And that, of course, last column, by last column, I mean this column here. There are 16 different things you can put here because each one of these entries here could be either 0 or 1 in general. So there are 16 possible functions. So now, how many for n inputs? That's for 2 inputs.
Then it will be simply 2 to the power 2 to the power n.
2 to the power? Then?
2 to the power
How
n.
much?
2 to the power n. 2 to the power
Right.
2 to the power n.
Yeah, it is 2 to the power 2 to the power n because there are 2 to the n possible input combinations. For each of them, each and every one of them, you have 2 possibilities in the output. So you should realize these numbers actually increase exponentially fast. In fact, not only exponentially. 2 to the n increases exponentially with n. 2 raised to the power 2 to the n actually increases super exponentially, way faster than exponential growth. So number of distinct possible functions you can have is say 4 inputs is 2 to the power 16. Okay. So that's already 2 to the 6 is 64 and 2 to the 16 is 64,000 or actually 64 times 1024. So roughly 64,000. So even with 4 inputs, there are nearly 64,000, in fact more than 64,000 possible functions. So this really can get pretty large in number. Thankfully, Boolean algebra allows us to sort of work out these functions rather easily, even with 4 inputs. And that's exactly the subject of the kernel map technique that the second video that I've already uploaded is all about. And that's a very, very important technique. But thankfully, what I'm going to talk today will not need that technique. You will definitely need to know it because it's very important and very useful. So today, what I'm going to talk about are 3 very advanced circuits. The first advanced circuit, okay, I've already drawn these circuits somewhere. Let's simply because drawing them takes a lot of time. Okay, this is called a binary to decimal decoder. Okay, and looks like a this side looks pretty simple. These are all AND gates. there are actually 10 AND gates here. Why 10? Basically because the output essentially signifies decimal. Okay. So very often you would have numbers like, say, binary inputs like 0, 1, 0, 1. Now, if you were to treat this as a binary number, how much will this be? What is 0, 1, 0, 1 in decimal?
5.
5 because this stands for 1. This stands for 2, but there are no 2s. Just like 173 would really be 3 units, 7 tens and 100s. In binary, you do the same thing except that you don't say tens and hundreds. What you have is ones, twos, 2 squares, there is 4s, 8s. So 1 ones, 2 fours, 1 fours. So 4 and 1, 5. Fine, so this is 5. So what I want is to create a circuit where if I give 0, 1, 0, 1 to the inputs, suppose I gave 0 to A, 1 to B, 0 to C, 1 to D. These are the 4 inputs. Suppose I gave that. The output, well, there are 10 possible outputs here. What will happen if I give 0, 1, 0, 1 to this one is that only Y5 will go high. All the rest will stay low. That is, it essentially says, okay, out of all these possible binary inputs, it's essentially checking what decimal number it conforms to, and makes that particular decimal output labeled by that particular decimal number high. So how does it work? Now, of course, this side is pretty easy. These are all 4 input AND gates, which means the output will be high if and only if all the inputs are high. And here, what you have are actually 4 and 4. So I've deliberately drawn the original A, B, C, D lines using red. And each of the A, B, C, and D have been passed to a NOT gate, as you can see here. And the output are these blue lines here. So this red line stands for A, this one for A bar, this one for B, this one for B bar. You have C, the blue line is C bar, D, D bar, right? So when I put in 0, 1, 0, 1, okay, which lines go high? Which lines have a high voltage? Out of these 8 lines, all 8 lines don't have high voltages, right? Which ones have high voltages? For A, for example, out of these 2, red and blue, which one is high?
Blue.
Yeah. For B, the red one is high. For C, the blue one is high. For D, the red one is high. Right? That's it. If I give 0, 1, 0, 1 as the input, that's what's going to happen. Blue, red, blue, red. Right? Now notice, for example, this particular AND gate is connected to all 4 blues. But are all the 4 inputs to the AND gate high now? Remember, the AND gate will produce a high output only when all 4 inputs are high. Otherwise, it's going to produce a low output. If you look at this first AND gate, it's connected to all the blue wires. Okay? Right? So are all the inputs to this AND gate high?
No, sir.
Of course not, because this one is high, A being 0, A bar is high, but B is 1, so B bar is low. So here, 2 of the inputs, B bar is low. Similarly, C bar is high, but D bar is low. So 2 of the 4 inputs of this AND gate are high and 2 are low. Of course, this means Y0 is going to be 0 because all 4 inputs are not high. To just check, Y5, well, is connected to the blue line here, red line here, blue line here, red line here. Are all its inputs high? blue,
Yes.
red, blue, red. Exactly. Y5 and only Y5 among the outputs, only this output is the output to an AND gate whose 4 inputs are high now. All the others have at least one input which is low. So the output is low for every one of them. It's high only for Y5. Now that's not an accident, of course. That 0101 is a binary way of saying out what decimal 5 looks like. And Y5 is the only one with all 4 inputs high. That's, of course, not an accident. And that is also the reason why you don't have to memorize this circuit. You can figure out the pattern very easily. Note Y0 is connected to blue, 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 right? What does it mean? Y0 will be high when all the 4 inputs are high, right? But what are the 4 inputs to Y0? To this AND gate with Y0 as an output? A bar. So A, B, C, and D, all 4 inputs have been sent through NOT gates and then put in here, right? And that, of course, means then and only then when A, B, C, and D are each low, or the input is 0, 0, 0, 0. Okay? Clear? Now, this should tell you how you would connect. Say, how would you connect the inputs to Y4, for example? Y4. Now look at this. I want it to light up only when the input binary reads equivalent decimal 4. Now what is the binary for 4?
0100.
Yeah, we are using 4-bit binary here because there are 4 inputs. So I have to always quote all the 4 inputs. 4, of course, the number 4, the decimal number 4 is 2 square, so that's 100. But because we are using 4-bit binary, it's actually read as 0100. Now, we want Y4 to be high when the input is 0100, right? That means we want the output to be high when A is low, A bar is high, B is high, right? But that means how would you connect them? You would actually connect the inputs to Y4 to the line which goes high when A is low, or the A bar line. That is the blue line for A. That is blue and red in our picture at least. Where would you connect the B? You would connect the B where it would go high when B is high, that is to the B line. So basically, if you think in terms of the colors here, this will be red, blue, red, red. Sorry, completely messed up. What it will be is blue, red, blue. So note that's exactly what we have done. The 4 inputs, blue, red, blue, blue. That automatically takes care of the fact that only when the input is 0100 will Y4 go up. But you can easily see the pattern here, right? If you read the blue as 0 and red as 1, this becomes even easier to read. The Y0 is connected to what? If you read blue as red, blue as 0 and red as 1, Y0 is just connected to 0000. That's of course the number 0. Y1 is connected to 0001, right? Which is why it's actually going to go high only when the input is 0, 0, 0, and 1, which of course is the number 1 in binary again. Y2 is connected to 0, 0, 1, 0. Then you have 0, 0, 1, 1, 0, 1, 0, 0. So you should realize that these are nothing but the numbers 0, 1, 2, 3, 4, etc. in binary that we have connected here directly using wires. Is it okay? And of course, how many possible input combinations could you have had? Yes?
16.
16. But how many do you need?
10 for decimal.
10 for decimal. That means we are not really making use of all possible combinations. Of course, you could have a binary to hexadecimal decoder, which actually is very useful in digital circuits. And if you want a binary to hexadecimal, you would actually use 16 output bits, so 16 AND gates. And here, for example, Y9 is connected to, okay, again, reading red as 1 and blue as 0, this is 1, 0, 0, 1, which is exactly what 9, the decimal number is. But then there's 1, 0, 1, 0, 1, 0, 1, 1, and so on, 10, 11, 12, all the way up to 15. Those extra 6 possibilities from 10 up to 15, they are not being used here because we are using a binary to decimal decoder. If you had tried to build a binary to hexadecimal decoder or binary to hex decoder, which is what people call it in the colloquial electronics language, they don't call it hexadecimal, they just call it hex. You would need 16 4-input AND gates and essentially follow the same pattern after this. Okay. One important point, usually I've drawn the lines in red and blue simply to make it easier for you to see what's going on. Of course, usually in circuits, people don't draw with color. You would have only black lines everywhere. But there's one very important thing that you have to notice, which is this. This wire, for example, is going all the way from here to here, right? Which one is this wire connected to? Is it connected to this wire, this red one or this blue one? I'm talking about the black wire at the very beginning, very top. Which one is it connected to?
So it is connected to A bar, means that not gate.
It's connected to only A bar, right? Not to the others. Now, here, there's a bit of convention involved. The point is, when you are dealing with decimal, dealing with binary circuit or Boolean circuits, the standard convention is if two wires just cross, okay? Like for example, this wire has crossed here. You can see my pointer, I hope. And then this wire has crossed here. This wire has crossed here. If they just cross, then you don't, if you have no special symbol drawn at the junction, you are just assuming that the two wires are not joined together. They're not connected. The reason why I'm saying this is when you draw analog circuits, usually the convention is this. If you want to show two wires which cross each other without being connected, you draw a bump. That bump actually is meant to signify that one of the wires is going either above or below the other wire. Okay? So you draw a bump like this just to ensure that people don't think that the two wires are connected. In analog circuits, usually it's a convention that when you draw something like this, you actually mean that there's a connection here. We often don't indicate the connection. The connection is supposed to be there. Okay, just hold on. Okay, this convention is not completely universal, but almost always when you want to show a connection in a digital circuit, the rule is you have to explicitly show the connection. Okay, that's universal. In all digital circuits, you show connections by showing a blob. Not necessarily a blob which is this big or drawn in color. And most often it will not be drawn in color. Definitely not in multicolor, the way we have drawn it. But the blobs are essentially to show that there are connections. That's simply because in digital circuits there are way too many wires. And if you had to show a bump every time two wires crossed, then things would become very, very messy indeed. The standard convention in digital circuits is if you don't show a connection, then there is no connection. Two wires which just cross each other without a junction shown are not joined. Okay, so that's the convention for digital circuits. That's the one we are going to follow here, at least. And for analogs, the rule is unless otherwise stated, if two wires cross like this, they're actually connected. If you want to show that they are not connected, you draw a bump either on the vertical wire or on the horizontal wire. It doesn't matter which one. But this bump signifies that the wires are crossing without actually touching each other. Okay. So are there any questions about this binary to decimal decoder? In particular about the pattern, the way in which you connect the inputs? Okay, I hope not. Let's go on to the next circuit. The next circuit, by the way, the previous one was a 4-bit binary to decimal decoder. It just decodes the binary digits, the decimal digits 0 to 9. And because you want to have 10 distinct possible outputs which you want to handle, 0, 1, 2, 3 up to 9, you must have at least 4 input bits, because with 3 you can only have 8 different input combinations. With 4, of course, you have 16. You can have 16, but if you want 10, you have to go beyond 3. So you have to, it will only work with 4 or more bits. Here we have just used a 4-bit binary to decimal decoder. Now, the next circuit sounds a bit complicated. It's called a 1 to 8 demultiplexer. Okay. And it's very much, okay, the reason why I'm talking about this right after the binary decoder is that actually this is almost identical to the binary decoder. Because if you look at, except for the fact that there we had, we wanted 10 possible outputs because we are doing binary to decimal. Here we are actually looking at 8 possible outputs in this particular circuit, Y0 through Y7, which means 3 inputs is fine. In fact, if you calculate the other way around, you say, okay, my circuit has 3 inputs, so there are 8 possible output combinations, so I'll have to have 8 outputs. Okay, that's the way you should argue. Of course, you could have a 1 to 16 demultiplexer, but there you would have 4 inputs A, B, C, and D. 5 inputs will give you 1 to 32 demultiplexer, and so on. So what does this really do? As I said, if you ignore the green line, this green bit here, the D and the connections to it, just hold on. Okay, sorry about that. Another emergency in admissions. Now let's get back to this. So we said this is essentially the binary to octal decoder with an additional thing built in. So binary to octal would have been 8 possible outputs, 0, 1, 2, 3, 4, labeled y0, y2, y1, y2 up to y7. 3 inputs, A, B, and C. Again, each of the 3 inputs doubled because you have one line, the red line for A, the blue line for A bar, similarly B, B bar, C, C bar. And if you look at Y0, it's connected to ABC exactly in the same way, to blue, 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 0, 0, 0. Here, Y1 is connected to blue, blue, red, 0, 0, 1. Y5, for example, is connected to red, blue, red, 1, 0, 1. That's 5. Okay. So this pattern is pretty straightforward. It's just exactly the same pattern as before. The only difference that has been done is now you have another input D. I'm just calling it D because ABC is gone here. Another input D, which actually is joined to each and every one of these AND gates, right? So D is just connected to all the 8 AND gates, AND gate inputs. So each of the AND gates are still, despite the fact that we are using a 3 input scenario, if there are only 3 of ABC, or the 3 control scenario, each of the AND gates have 4 inputs. 3 of them are connected exactly like in the decoder, in the blue, 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 red, blue, red, blue. That is 0, 0, 0, 0, 0, 1, 0, 1, 0, that pattern. And the 4th input to each and every one of these gates is connected to D. So now, question. If the ABC happens to be, let's say, 0, 1, 1, can you tell me what the outputs are going to be? What about Y0? What will Y0 be? Once again, remember, an AND gate produces a high output only if all inputs are high. So what will happen to Y0?
0.
0.
Y1?
Y1 will be 0, sir.
Okay, so in fact, you can easily check that all of them will be 0 except for
Y3.
Y? Y3. Well, Y3 actually, well, the point is all the others will be definitely 0. But what will Y3 be? Y3 is, for this gate, there are 3 inputs which are coming from A, B, and C. Actually, A bar, B, and C, right? A bar, B, and C. And the way we have, for this particular input combination, ABC equals 0, 1, 1, all 3 of these inputs is high. So what will the output be?
Output should be high.
No, because remember the Y3 actually has 4 inputs, right? Not each of the AND gates here have 4 inputs. 3 of them, A bar, B, and C are high, when A, B, and C are 0, 1, and 1 respectively. So 3 inputs are high. What about the 4th input?
The output will be what D will be.
Exactly. The 4th input depends on D. If D is low, then one input is low, the output goes low. If D is high, all 4 inputs is high, then the output goes high. Actually, what we are using here is this rather important Boolean result, which looks like a trivial thing to say if you think of dot as multiplication, but which it really isn't. A and 1 is the same as A always. If one input of an AND gate or 3 inputs of a 4 input AND gate are all 1, then the output is just the last or the other input. For the simple reason that whatever the other input is, that will be the output. If the other input is high, the output will be high. If the other input is low, the output will be low. End of story. So A and 1 is always A. So here what's happening is the way the decoder is designed, all the inputs to each of these AND gates here, except for one of them, in all of them, one input is guaranteed to be low, at least one input, if not more than one. That's how you have designed the decoder. That's exactly why the decoder only had one of the 8 outputs or 10 outputs in that case. One of them go high, everything else was low. Here what we are doing is we are not stopping there. We are actually putting in one more input to the AND gates. And what this does is essentially this input D is directed either to Y3 here. If input ABC were say 111, then D would be directed to Y7. Okay. If the input were 0, say 010, then D would be directed to Y2. So basically what you're doing here is by using those A, B, C, which are actually control inputs, you're controlling which one of these outputs get the value of D. You can send D to either Y0 or Y1 or Y2 or Y3 or any one of them from Y0 to Y7 just by changing the input. The input, if it's 000, D goes to Y0, everything else stays low. If it's 001, D goes to Y1, and so on. So you have to realize that what this does, this is actually at the heart of a digital computer, this kind of thing. Being able to divert a signal from one location to another just by changing your control signals, that is one of the major things that a digital computer really does in its inside. Now, there are many other things which are needed to build up a full-fledged digital computer. And I don't really have the time in the rest of the semester to talk to you about all of them. But we will indicate in the rest of this, in the next week's lectures, whatever we have left, we will essentially talk about circuits which essentially go into building up a digital computer, blocks which build up a digital computer. If you're interested, you can then go and read up books and figure out how exactly the digital computer built. That's different from how you program it or how you use it. How is it that the electronics inside a digital computer is actually connected together so that when you put in a given sequence of zeros and ones as its input, it magically can calculate, say, the Fibonacci number, the 10th Fibonacci number. What is there inside? What actually goes on? We are not in a position to talk about that because that would have taken 2 semesters at least, just that much. I'm doing this in 2 weeks. So I'm just going to give you some basic indicators of circuits. But this is one kind of circuit which is very important. Being able to redirect a signal from one place to another just by using the controls. Now the final circuit that I'm going to talk about today, in a way, is an opposite of that. It's called a multiplexer, not a demultiplexer. So this one is an 8-to-1 multiplexer. Okay. 8, simply because once again you are using 3 inputs, 8 possible input combinations, so you have an 8-to-1 multiplexer. You wanted to build a 16-to-1 multiplexer, you would have to use 4 inputs. Pattern would be exactly the same. And here, note what we have done. This multiplexer is again a circuit. If you ignore this final thing here, this thing is an OR gate. If you just ignore the OR gate here, the rest of the circuit is very similar to the demultiplexer, right? Although the multiplexer and demultiplexer, by their very names, they seem opposite of each other. You would realize that if you forgot about this part, the part to the right of this line, say I'm drawing this line here, you ignore the part to the right of this line, then the circuits are almost identical except for one difference. What's the difference? Well, not one difference, actually 7 differences. But what's the difference?
The Ds are not same.
Yeah, earlier you had only one D which you were directing to each one of the 8 inputs. That is, you had 8 AND gates, each of them were 4 input AND gates, 3 of them were coming from the control bits. 1 was coming from elsewhere, and you were connecting all of those extra inputs of the 8 AND gates, you were connecting all of them, each and every one of them, to a single input D. So whenever, depending on whatever the control bit said, the output would get directed to that. Okay. Here what will happen? Here what will happen is something like this. If ABC, for example, what I have written is 110. 110 is actually the decimal number 6, right? 4 plus 2 plus 1. 4 plus 2 plus 1 into 0. So that's 6. Okay. So if ABC were 110, then only the 6th one, the connect one which is connected to D6, actually the 7th one, right? Because we are counting starts from 0 here. Only this one, which is connected to red, blue, 110. This one will have D6 as the output, right? What will the output of all the others be? So for example, what will the output of this AND gate be when ABC is 110?
0.
It's bound to be 0 because it doesn't matter what D0 is. Because one of the 3 control bits, look here, the control bits are all connected to A bar, B bar, C bar. If ABC are 110, then C bar is high, but A bar and B bar are definitely low, right? So A bar, B bar, C bar will definitely be low because one or more of the inputs in this case is low. So it doesn't matter what D0 is, the output here will be low. The output here will be low for the same reason. The output in this one will be D6. Everything else will be low. But now what you are doing is taking these 8 outputs and putting them through an OR gate. So this is an 8 input OR gate. Fine, there's nothing really magical about that. It means it's a gate which will be high whenever any one of its inputs is high. But now all 7 of the inputs are low, so the output will be exactly the same as D6. If D6 is low, every input is low, the output is low. If D6 is high, then one input is high, the output is high. So what is being done here? What you have done is if you put in 110, the output here is going to be D6, right? If you put in 111, the output will be which one?
D7.
Yeah. 011,
D3.
D3. Okay, so now can anybody tell me what is the good of this circuit? What can you do with this? What's the practical use of this circuit? Okay, let me give you a hint. Suppose I wanted to implement a Boolean function with 3 inputs, A, B, and C. And of course, 3 inputs means there are 8 possible input combinations. And I prefer writing the combinations in this order for one very simple reason. If I write it in this order, I can make sure that I've covered all of them. Simply because these are not just the numbers 0, 1, 2, 3, 4, 5, 6, 7. So it's easy to keep on counting from starting from 0 and increasing by 1 at every step. And that's exactly what I've done here. The output, let's say Y, the output that I want is something like this. I'm just making something up. Say 0, 1, 1, 0, 0, 0, 0, 0. So this is a particular Boolean function. How many Boolean functions can you have with 3 inputs? We talked about that a while ago.
64.
Yeah, to the 8. Right? With 3 inputs, you can do to the 8. With 4 inputs, you can do to the 16 and so on. So we are doing it with 3 inputs here. But now, let's say I do one thing. I make this one single demultiplexer circuit. In fact, you don't even have to make this circuit. This is available usually as a integrated circuit chip. So you don't even have to make anything. This is just available to you. Now, if you have this one circuit And then you do one thing, you just apply 0 volts to D0. So these are inputs, right? These are control bits, these are inputs. Now here you just put in 0, 1, 1, 0, 0, 0. I can't see the others. Yeah, all others are 0. Okay, fine. I put this in. Now what will the demultiplexer do? If the input is 0, 0, 0, it will give you D0. That is, it's going to give you 0. If the input is 0, 0, 1, it's going to give you D1. That is 1. Right? So, in fact, this demultiplexer will exactly reproduce this particular truth table. That is this particular Boolean function. You want to create this, you have this demultiplexer, you just give the appropriate inputs, you've got this circuit. So now can you see what's the advantage here? How many Boolean functions can you have with 3 inputs again? Yes?
So 2 to the power 8, which is 216.
To the 8. Right? To the 8 is actually, how many are there? How many is 2 to the 8, by the way? Actually, the number that was quoted a while ago was not right.
256.
It's 252. It's 252, not 64. Okay. 64 is 8 to the power 2. 2 to the 8 is actually much larger. Right? 64 is actually 2 to the 6. There are 252. Sorry, 56, 256, sorry. 256. Yeah, 256 distinct possible Boolean functions you can have with 3 inputs. How many circuits do you have on this paper? Only one. But that one circuit can implement each and every one of the 256 possible Boolean functions. All you have to do is change the input table. All you do is write down the truth table, whatever is on the output column, just apply those to D0, D1, D2, D3, D4, D5, D6, D7. And you're done. Your circuit is going to implement that particular Boolean function. So you don't have to change the circuit to implement another Boolean function. You can just apply a different set of inputs here, will implement another Boolean function. It's almost like magic. 256 different Boolean functions, 256 different circuits, all can be implemented with this one single circuit. Yeah. Because the moment you're putting 0, 1, 1 and 0, 0, 0, 0, 0 as the inputs D0 through D7 in this circuit, what it's going to do is it's definitely going to give you this truth table. Or 0, 0, 0 should have given you D0, but D0 is fixed at 0, so it's going to give me 0. For 0, 0, 1, it should have given me D1, D1 is 1, it's going to give me 1. So any other truth table that you want, all you have to do is change these input voltages and your output will definitely produce that output. Okay, that particular truth table. So this is 256 circuits rolled into one, a 4-input demultiplexer. 4-input multiplexer, not demultiplexer. 4-input multiplexer would be essentially 16 to 1 multiplexer. And 16 to 1 essentially means that it's going to be able to reproduce 64,000 different circuits in one. But does that mean that you don't have to learn about other Boolean circuits at all? The answer is no. You do have to learn about other Boolean circuits for the simple reason that this may not be very efficient. There are much simpler or cheaper ways to create most 3-input Boolean circuits. Not this one. Okay? And could be faster. The circuits could be faster if you make it differently. Oh. So this is a circuit which is great for prototyping. For example, if you want to play around with different circuits and see whether what you really want to do is achieved by this particular circuit. You don't want to build a new circuit every time you want to play around with the circuits and change them. You can just use a single multiplexer. You can mimic all circuits with that. But for the sake of efficiency, once you're sure that this is the particular Boolean function you really want, you would usually go in for some other design, usually. But this is very, very useful for many purposes, including as simple as this one, that you can mimic, or you can make it work like any circuit you want. Okay. So are there any questions about this? If you just think about it a bit, all these three circuits that I talked about essentially all start with this basic idea. Okay, binary to decimal just had one extra input because you needed 10 outputs. But if you just ignore the A in this picture and labeled B, C, and D by ABC respectively, then you have a binary to octal decoder. And just by connecting a single input to the fourth input of each one of the ANDs here, along with this 8 to 1 decoder, 1 to 8 decoder, or rather binary to octal decoder, you could simply get a 1 to 8 demultiplexer by connecting 8 different inputs and finally threading everything out through a single OR gate. Now you have only one output, and that's the 8 to 1 multiplexer. Multiplexers, by the way, anybody knows what a multiplexer is in actual technical language? What is a multiplexer? In music, people use multiplexers. Or, of course, you have multiplexers. That's something which everybody knows, right? So what exactly is a multiplex? Is where many different functions, many different things come together as one. That's why it's a multiplex, not a single screen thing. Okay? And that's exactly what is happening here. It's taking 8 possible outputs, basically, and then combining them into one, and mimicking 2 to the 8 different circuits. So any further questions about this? If not, we will call it a day today and meet you again on Monday. And remember, Tuesday's class test.